The power developed by an engine depends on the pressure sequence in the cylinder. The output of an engine is dependent on the relation between pressure and volume in the cylinder during compression, combustion, and expansion. For each separate cylinder, the gas process could be described by a curve, the so-called PV diagram or indicator diagram. The diagram shows that the pressure is almost equal to the scavenge air pressure when the scavenge ports are uncovered. The exhaust valve and scavenge ports are then closed, the air is compressed, and when the fuel is injected and ignited, the pressure will rise rapidly and remain at maximum during continued injection. After injection, the pressure in the cylinder falls to exhaust pressure and, during the exhaust period, to scavenge air pressure. Scavenging, compression, combustion, expansion, exhaust, and back to scavenging. The power developed by an engine depends on the pressure events in the cylinder. The pressure events can be recorded by means of an indicator connected to an outlet from the combustion space. The combustion chamber pressures can be measured by a PMI system supplied from MANdiesel. The PMI system replaces the traditional indicator and indicator drive. The PMI system allows the engine operator, through high qualitative data collection, to further refine the performance and reliability of the diesel engine. Essentially, the PMI system ensures that the load and balance of cylinders is kept within predefined limits with regards to their mean indicated and maximum combustion pressure. The PMI system is designed to produce reliable calculation of mean indicated cylinder pressure and other performance data that require the accurate pressure measurement of cylinder pressures and detection of the crankshaft position. From the indicator diagram, the so-called indicated output can now be computed. At any given piston position during the compression stroke, there's a certain pressure, P, acting on the piston top, if the piston travels a short distance further, corresponding to delta V, and if we ignore the minimal change in pressure, the amount of work done, delta A, will be given by the pressure multiplied by the change in volume, or P times area below the part of the compression line corresponding to delta V, and the same applies to every single part of the compression curve. That's to say that the whole area below the compression line represents all the work that the piston must perform to compress the air in the cylinder. During the expansion, the piston pressure acts in the same direction as the piston's moving, so the piston receives an amount of work. And it'll be seen in the same manner as before, that the amount of work received is represented by the area below the expansion curve. The amount of work transmitted to the piston during a full engine revolution must therefore be the difference between that delivered during the compression and that received during the expansion. In other words, it's given by the area between the curves. Thus, A equals sigma P multiplied by delta V. The equation can be rearranged to express the temperature T, direct for an arbitrary piston position.